Well, good afternoon. Thank you for coming. My name is Jim Toney. I work at a small company in Columbus, Ohio called Shrico. We do electro-optic devices and systems for a variety of applications. Before I get started, I want to take care of one little thing. I'm going to pass around these slips of paper. Please write your name and affiliation on it and pass them forward to the chairman. And we're going to have a door prize drawing at the end. So what I'm going to talk about today is direct measurement of electric fields based on the linear electro-optic effect. Now, since this is a sensors conference and not a photonics conference, I'm going to spend a few minutes going over the basic principles of operation of electro-optic devices and systems, then talk about the basic device structures that we use for electric field sensing and some of the system considerations. And most of what I'm talking about today is expounded upon in more detail in the book that's pictured up there called Lithium Niobate Photonics, which is available in various places. All right, so when I talk about measuring electric fields, what specifically do I mean? What part of the electromagnetic spectrum am I talking about? What sort of field strength? Well, it varies enormously with the application. Sometimes people are interested in measuring very low-level signals like microvolts-per-meter. Sometimes people are interested in measuring very high field strengths like megavolts-per-meter. Some people want to measure very high frequencies, microwave, and even into millimeter wave. Some people want to measure very low frequencies, close to DC. And one of the strengths of the electro-optic approach is that it's applicable pretty much across this range of field strengths and frequencies. Now, of course, not all in the same device. If we could make one device to measure from microvolts per meter to megavolts per meter and from DC to terahertz, we would. But of course, no sensor has that kind of dynamic range or bandwidth. So you kind of have to target the sensor, optimize the sensor and the instrumentation for the target application. So the basic idea of electro-optic modulation, although the physics is different, conceptually it's essentially the same as modulating an RF carrier by, say, an audio signal. You have a carrier, which in this case is optical frequency, and some modulating signal, which in this case can be anywhere from DC up to well into the microwave region. And the two of those things mix in the electro-optic device, and that modulating signal is impressed basically as an envelope on the carrier. Now, the physics of operation is that the electro-optic crystal, its refractive index changes when it's subjected to an electric field. So that's what I mean when I say electro-optic. Sometimes people use electro-optic very broadly to mean anything in physical optics. I mean a change in refractive index in certain kinds of crystals under the application of an electric field. So if the refractive index changes, then there will be a phase difference impressed on any optical carrier passing through that crystal. And there are various device structures that you can use to translate that phase difference into a difference in the transmitted intensity. Excuse me for 1 second, I'm going to set my timer to make sure I don't go over. Okay. So here's a basic block diagram of a typical electric field sensor system using an electro-optic device. Since it's an optical device, we have to have a light source, which in most cases is a laser, although other kinds of sources like superluminescent diodes or ASC sources can be used as well. And light from the source is connected to the sensor, which is placed at some remove from the instrumentation, through in most cases, a polarization maintaining fiber optic cable. There's one thing about electro-optic devices, they're highly polarization dependent. So you have to control the polarization of light that's going into the sensor. Now, once it comes out of the sensor, then we don't care about the polarization anymore, unless you're doing some kind of coherent detection, which we typically don't do. So the return fiber can just be an ordinary single mode fiber. So it's connected to a photoreceiver that demodulates the signal, recovers the original electric field waveform. That gets amplified and then acquired either in the time domain or the frequency domain, depending on the application. Now, one thing that's shown here that's kind of optional is sensor bias control. Depending on the specific device geometry, you may or may not be able to do bias control. It may or may not be feasible, let's put it that way. So I'll say a little bit more about that issue of bias, or maybe I should say operating point of the sensor later on. So I mentioned the electro-optic effect is a change in the refractive index, but you should keep in mind that most electro-optic materials are birefringent. That is, they have at least two refractive indices depending on the polarization of light. So not only is the refractive index dependent on polarization, so is the electro-optic effect. So the electro-optic effect can actually be quite complex. It's a 6x3 tensor. So in principle, there are up to 18 elements, but no crystal has 18 independent electro-optic coefficients. Depending on the symmetry of the crystal, the number of independent non-zero ones will be much less than that. For lithium niobate, it's 4. Now, lithium niobate and its LT is lithium tantalate, a closely related material. They call it its fraternal twin. These happen to be a case where the best case is also the simplest case. One of the few times when nature has been kind to us in that way. Because for these materials, if you apply the electric field along the z-axis, which is also called the optic axis, it's the symmetry axis of the crystal, then the cross terms in the electro-optic tensor are all 0. The off-diagonal terms, you might say. So it becomes simple. You just get a change in the two refractive indices. NO is the ordinary wave for light polarized in the plane perpendicular to the optic axis. NE is light polarized parallel to the optic axis. And each of those changes in proportion to its electro-optic coefficient. So that's either R13 or R33. And also times the cube of the refractive index. So that's the electro-optic figure of merit. It's actually N cubed times R. In niobate and tantalate, the electro-optic effect for light polarized along the optic axis is about 3 times as strong as the other one. So whenever possible, that's the one you want to use. Okay, so to get the strongest electro-optic effect for lithium niobate or lithium tantalate, you want both the light wave and the modulating field to be parallel to the z-axis. The other thing you have to keep in mind in thinking about electro-optic materials, not only their optical properties, but also their electrical properties. And one thing in particular, most electro-optic materials, with the exception of the semiconductors, have very high relative permittivities or dielectric constants. Given some representative values here for lithium niobate. And again, it's anisotropic. Okay, so this number of 43 for RF frequencies, or about 78 for DC, that's for light polarized in the X or Y direction in the plane perpendicular to the optic axis. And these numbers of 28 or 32 are for light polarized along the optic axis. And the other thing that becomes an issue if you're dealing with relatively high frequencies, the RF loss can be significant. The RF loss tangents can be up to 6 times 10 to the minus 3 as you approach millimeter wave frequencies. So for that reason, there's a lot of interest in preparing thin film electro-optic materials on more RF-friendly substrates like quartz, for example. So if you work with semiconductors, you know that thin film technology is indispensable, right? This is how you make the devices to do what you want to do. You deposit different layers by epitaxy of materials at different band gaps or different doping. We'd like to be able to do that with lithium niobate, but it's just never really worked. People have tried to do epitaxy of these materials, and they've just never been able to produce thin films that have the same electro-optic and nonlinear optic properties as bulk crystals. So the current approach that most people are working on is to deposit films, or maybe I should say prepare films, by what's called crystal ion slicing, or sometimes it's called smart cut. It's the same technology that they use for SOI. You exfoliate a thin film by ion implantation and then transfer it to another substrate. And this can be done up to about 10 microns in thickness with a high energy ion implanter. Any thicker than that, it becomes more practical just to take a bulk crystal and mechanically thin it down. All right, one more basic element of lithium niobate device technology that enables a wide range of device functionality is ferroelectric domain engineering. And these materials are ferroelectric, which means they have a permanent electric dipole moment. So it's by analogy to ferromagnetic. Ferromagnetic material has a permanent magnetic dipole, which you can reverse by applying a strong magnetic field. Ferroelectric has an internal electric dipole, which you can reverse by applying a strong electric field. And you can do that locally. You can pattern ferroelectric domains to make a variety of programmable, essentially, electrically controllable optical elements. So for example, here's a really basic example. If you were to domain invert a circular region, okay, so all the surrounding region is polarized one way, this circular region is polarized the opposite way, the electro-optic coefficient reverses in sign. So you just apply a continuous electrode, apply a uniform electric field. The material out here, well, its refractive index will go one way, and the material in the domain inverted region, its refractive index changes the opposite way. So you get an index contrast between the two regions, so you've got a little programmable lens. Now, the last basic element of device technology that I need to mention is waveguides. Most of the devices we do are not bulk crystals, but they're integrated optical devices, devices with waveguides. Again, in semiconductors, the way they do this is by epitaxy, depositing layers of different refractive index. We can't do that in Niobate, so the way we make waveguides in Niobate is by diffusing in dopants. And the two most commonly used ones are just protons and titanium ions. And so the two basic waveguide, most commonly used waveguide technologies in lithium niobate are annealed proton exchange, where you just literally dunk the wafer in acid at elevated temperature for a certain amount of time. Protons from the acid diffuse in and displace some of the lithium ions. And then you anneal that at a somewhat higher temperature to get back the electro-optic functionality. So these make very nice low-loss waveguides. One thing about them, which could either be a feature or a deficiency depending on what you're trying to accomplish, it only guides one polarization. It only guides light parallel to the optic axis. It doesn't raise the refractive index for the other polarization. So if you want a device with a built-in polarizer, that's great. But if you're trying to do, say, a polarization controller where you need to guide both polarizations, that won't work. So the other basic waveguide technology that people use is titanium diffused, which is a higher temperature process. It's about 1,000 degrees C. Has the advantage that it guides both polarizations. Its major disadvantage is poor resistance to optical damage or photorefractive effects. You can't put much light through it, especially at short wavelengths, before its performance starts to degrade. So one thing we're currently working on is zinc oxide diffused, which kind of combines the advantages of both. It will guide both polarizations, but it has good optical damage resistance. So this is a good technology for high power devices when you need to guide both polarizations. And RPE, reverse proton exchange, that's mainly used in nonlinear optics. It just improves the nonlinear optical conversion efficiency. It kind of buries the mode below the surface and gives you better mode overlap. So I mentioned there are a number of device structures you can use. The workhorse device is the Mach-Zehnder interferometer. Right? Maybe I should say the optical waveguide implementation of a Mach-Zehnder interferometer, where you have light coming in on an optical fiber, going into a straight channel, and then it splits into two channels, two arms of the interferometer, propagates for some distance, and then it's recombined and comes out on another fiber. And so if everything is perfectly symmetrical here, these two waves, that is the waves in the two arms of the interferometer, should recombine in phase, add constructively, and you get out the same power that you put in, minus whatever insertion loss there was. On the other hand, if there's a phase shift between the two arms, let's say a pi phase shift, 180 degrees, or half a wavelength difference in optical path, then they'll recombine destructively. They'll cancel each other, and you'll get no power out. And anywhere in between the two, it's a cosine function. So how do we get the phase difference between the two arms? Well, of course, we apply an electric field. I'll say a little bit more about the details of how we get a change in one arm that isn't canceled by the change in the other arm. But this is the same basic device structure that's used to make modulators, high-speed modulators for telecommunications. So the two basic performance parameters or device operating parameters. One is called V pi, the half wave voltage, which is the voltage you have to apply to get a pi phase shift. Or here, since we're talking about electric field sensing, you could just replace the V's by E's, call it E pi. What electric field do you have to apply to get that pi phase shift? The other thing that's overlooked sometimes, but it's really important, is the bias point or operating point. The performance of the device will depend on what that bias point is. Now you might think, well, it's completely symmetrical. The bias point should be 0, right? Well, it's not completely symmetrical because we're talking about a device that's maybe centimeters long, and it only takes an optical path difference of half a wavelength, fraction of a micron, to go from constructive to destructive interference. It's not that symmetrical. You know, there are variations in material properties and geometry just due to fabrication. So you have no idea what bias point it's going to be sitting at. Now with a modulator, they control that. They just have a DC electrode, apply a DC voltage to move it to the bias point that they want. With electric field sensors, the whole point is to try to get away from having electrical cables and things in the region where you're trying to measure the field. And that's the main advantage of these dielectric type sensors. So we tend to avoid that. So with electric field sensors, we tend not to do bias control, but I'll show you later how we can just do bias drift compensation. So this just illustrates the effect of varying the bias point. So this shows the output power, the optical power coming out over the optical power in, versus time when the device is driven by a sinusoidal waveform. Okay, so if it's sitting at what's called the quadrature point, where phi 0 is pi over 2, that's the point of maximum linearity. And you get pretty good fidelity here. This is a large signal response. But you put a sine wave in, you get something out that looks pretty much like a sine wave. If you're at a different bias point, say pi over 4, you get a distorted waveform. As it gets to the maximum here, it saturates. If it was at a higher bias point, or we went even higher in drive voltage, it would actually bend over because it's a cosine function, it's cyclical. Right, so if you're at a bad bias point and you have a large signal amplitude, you will get distortions. Another thing that can happen that's kind of interesting, if you're sitting right at the null, that is phi 0 of pi, or 0, if you're sitting at the peak or the null, you'll actually get frequency doubling. Okay, the slope is 0 at that point. The device has a quadratic response, and you'll get perfect frequency doubling. I'll show you a real example of that in a little while. So here's another view. It's pretty much the same as the schematic I showed you before, but just the basic idea of a fiber optic link. And so electric field sensor, you can just think of as a fiber optic link, but instead of driving the electrodes with a voltage, we don't have connections to it, we just place it in the electric field. Otherwise, it's the same thing. And so again, you have a light source, the modulator, you're driving the modulator, transmitting over a fiber optic cable to a photoreceiver that demodulates, and you capture the signal either in the time or frequency domain. So what's the gain of a fiber optic link? So this shows all the factors that affect the gain. Of course, it depends on the optical loss, how much optical power you're using, the properties of the modulator, what its V pi is, what bias point you're sitting at, the responsivity of the detector, and if we're just talking about an unamplified link, if we just imagine the photocurrent directly going into a resistor, then you would multiply that by the load resistance. So it's kind of revealing if you put this on a dB scale, because you see this constant term, and that factor of 1,000 is because I'm putting the input power in dBm, or in other words, milliwatts. Okay. So to put it in watts, you divide by 1,000. So that gives you a constant term of minus 56 dB. All these things are on the order of 1, which you multiply by 20. So we've got 20 minus 56. We're at about minus 36 dB. And then you have to make up for that by whatever optical power you can put in. And so it's difficult, actually, to get above unity gain, or even close to unity gain, in a fiber optic link without amplification. And you would need about 18 dBm of net optical power. That is the optical power you put in minus the optical loss. And it's not that hard to get a laser that can put out that kind of power. The harder part is finding a good high-speed photoreceiver that can handle that much power. So if you modulate an optical wave with an electro-optic modulator, and then look at it on an optical spectrum analyzer, it'll look pretty much like amplitude modulation of an RF carrier. You have the carrier. So this is a example measurement that I did with a 1550 nanometer diode, laser diode. So you have the carrier, and I was modulating this at 10 gigahertz, which translates to about a tenth of a nanometer wavelength difference. And you see the little side lobes that show up at plus and minus 12 gigahertz, or about a tenth of a nanometer. If you then put that through a direct photoreceiver, in other words, a square law detector, something that just responds to the optical intensity, that will demodulate this and just recover the RF frequency at 12 gigahertz. Now that assumes the power is relatively low. It's low enough that the response is essentially linear. Okay, so here's an example. The first one is at relatively low power. And this is at much lower frequency because I wanted to be able to show the harmonics. So I'm driving it at 200 megahertz. I get an output signal at 200 megahertz. Essentially all the power is in the fundamental. Turn up the modulating voltage, and now I get significant power in the harmonics. In this case, mainly in the third harmonic. And that's going to depend on what bias point you're sitting at. So this was the case where it was sitting very close to the quadrature bias. So almost all the distortion goes into third order. Well, I should say odd orders, mainly third order. But if I captured it over a wider frequency range, you'd see something at fifth order, seventh, and so forth. All right, so if you bias it at the optimal or the highest linearity point, you'll get only odd order distortion. But then I changed the bias point, so it was biased at either the peak or the null. This says phi 0 equals 0, so that would be biased at the peak. And you see I get all even order. In fact, I don't even have a fundamental anymore. Okay, so this is that quadratic response. All right, so if you're biased near the quadrature point, you'll get mostly odd orders. If you're biased near the peak or null, you'll get mostly even orders. All right, so the linearity of the modulator is what controls the upper end of the dynamic range. What controls the lower end, of course, is noise. And the noise contributors, well, there are three major ones. Where we'd like to be most of the time, if we can, we'd like to be limited by shot noise in the detector, because that'll give us ultimately the best signal-to-noise ratio we can get. So at relatively high optical powers, and what constitutes relatively high depends on the characteristics of the detector, but then you'll be limited by shot noise in the detector. At lower optical powers, you may be limited by thermal noise, or KT noise, or Johnson noise. At RF frequencies, it becomes more difficult to get receivers that are shot noise limited, or where you can easily achieve shot noise limited operation. So at higher frequencies, we tend to be limited by KT noise. At intermediate frequencies, say audio to low RF, we tend to be limited by shot noise. And at very low frequencies, low audio, close to DC, we tend to be limited by the noise in the laser, because that tends to have a 1 over F characteristic. All right, so finally, having covered the preliminaries, we're going to talk about the application of electric field sensing. So, given the limited time, I'm mainly going to talk about the Mach-Zehnder interferometer as an electric field sensor. But at the end, I'll mention a couple of alternate device geometries that people have experimented with. So some of the advantages of photonic electric field sensors as opposed to, say, a metallic sensor. One is what I pointed out when I was showing you the block diagram. The sensor can be far removed from the instrumentation. And it's connected only by optical fibers, which people would much rather do than have, say, 100 meters of coaxial cable running through the region where you're trying to measure the electric field. And being all dielectric, it tends to perturb the electric field that you're trying to measure less than metallic sensors. It's not non-perturbing, but it's less perturbing than metallic sensors tend to be. And great thing about fiber optics, of course, is they have very high immunity to electrical noise, essentially infinite. They're not going to pick up interference the way coaxial cables might. And because they're all dielectric construction, or at least they can be, they can withstand very high field strengths without being damaged. So we can put these sensors in fields of megavolts per meter, and they'll survive just fine when a metallic sensor might get damaged due to arcing. Okay, so this is a third variant of the block diagram of an electric field sensor system. Here, I'm showing a typical setup for making, say, antenna measurements. So again, we have the laser connected to the sensor by a polarization maintaining fiber cable, back to the receiver through a single mode cable. And here, I'm showing the use of an RF network analyzer, which would be driving the antenna, and then you measure the response. So you can actually make coherent frequency domain measurements, which you can then transform to get a time domain response. So the only difference between this and the picture I showed you earlier of a fiber optic link is now instead of applying a voltage to the device, we're just placing it in the electric field. So it just becomes an issue of how does that external electric field translate into the internal field in the crystal? Because that's what actually determines the response of the device, the internal field in the crystal. And that's actually going to depend on the orientation and shape of the crystal. So you have to decide when you're making a sensor, are you going to use an X-cut crystal or a Z-cut crystal? Most of the time we use X-cut, primarily because it's more stable. Lithium niobate and lithium tantalate are pyroelectric materials, and that pyroelectric voltage, due to temperature changes, develops between the plus and minus Z faces. So with Z-cut devices, you get a lot of instability because of that. Minor temperature changes will cause it to drift quite a lot. But the one advantage of Z-cut, which pays us back for the problems that we have with instability, is the ability to do domain engineering. So we can use some more sophisticated device structures. But how the external field translates to the internal field in the crystal will depend on whether you have a Z-cut device or an X-cut device. Because we're dealing with thin wafers. Now if it's a cube, a bulk crystal, then it's probably not going to matter. But with the thin crystals that we use, it's going to be quite different, just because of the electric field boundary conditions, right? If you orient it this way, you have a long, skinny crystal oriented parallel to the electric field, then the boundary condition is that the tangential component of the electric field is continuous across the boundary. So basically you get the same field inside the crystal as outside, if the crystal is very thin and long. But on the other hand, if you have this geometry, a Z-cut sensor, then it's the normal component of D that's continuous, right? Which means the electric field gets reduced by a factor of the permittivity, the dielectric constant, which, as I showed you before, is pretty high for niobate. So it's a factor of about 30 that the field is reduced with a Z-cut sensor. So that's the other reason we tend to avoid Z-cut sensors. They just have lower sensitivity for that reason. Now, one more thing, the X-cut sensors tend to be much more strongly orientation dependent. This will not respond significantly at all to a field that's oriented horizontally, whereas this one will tend to respond almost equally to the vertical and horizontal fields, because the vertical field gets reduced due to the boundary condition, the horizontal one doesn't. And people tend to like sensors that are orientation dependent, because they want to know what the direction of the field is, not just its amplitude. So they might use multiple sensors with different orientations to pick out the different field components. So these are some simple electrostatic models that I did to show the orientation and shape dependence of the internal field versus external field. So the one on the left would be for the X-cut crystal, as the thickness is varied. So starting at the outermost curve here, where it's a relatively thick crystal, you see it perturbs the external field somewhat. And, I'm sorry, the one on the left is the Z-cut, my mistake. Yes, yeah, the one on the left, I'm sorry, is the Z-cut. So again, if it's rather thick, it'll perturb the external field quite a bit. And the internal field will not go to that value that I mentioned before of 1 over epsilon z quite. As you make it thinner, as we go this way, the perturbation of the external field gets less, and the internal field approaches this value of 1 over epsilon sub z. So that justifies what I said a minute ago. If you have a wide, thin sensor in a Z-cut, the internal field essentially will be the external field divided by the permittivity. The one on the right shows x cut. And this is a little harder to follow because instead of varying the thickness, I varied the width. But it's the width to thickness ratio that matters. So as we go, let's say from the inside out, the width is increasing, so the width to thickness ratio is increasing. The internal field approaches 1. That is, the ratio of internal to external field approaches 1. So again, if you have a long, thin sensor, it's a good approximation to say that the internal field equals the external field. Now the question arises, how are we going to use a Mach-Zehnder interferometer to sense an electric field? Because the electric field is the same everywhere, right? It's going to be the same for both arms of the interferometer. So how do we get opposite delta n's in the two arms? One way to do it is by domain inversion. If you domain invert the material in one arm of the sensor, then it experiences a uniform electric field. Well, refractive index of one arm will go up, the other one goes down, so you get a delta n between the two arms. So that's a way of making a true electrode-free sensor. You don't need any metallic electrodes. But you have to use a Z-cut, which makes it rather unstable, so we tend to avoid that. So if you want to make an X-cut sensor with an MZI, you have to use an electrode. Now it's not as bad as putting, a big metallic waveguide in the region we're trying to measure the field. This is a small region. This is less than a micron thick over a region of a few millimeters. But you put a little dipole type structure right on the lithium niobate chip, so that the waveguides are running here in the gaps between the electrodes. So you can think of this as being the plus, this as being the minus, and if we had a wider view, you'd see this wraps around. Okay, so this is also plus. All right, so the field on the upper arm is going, let's say, down. The upper arm then would be going up. So now we have oppositely oriented fields in the two arms. So again, we get opposite delta n's. Okay, that's called push-pull operation. Now with a structure like that, it becomes difficult to do an accurate model and know what the response of the sensor is going to be for a given electric field input. So we tend to just do it by calibration. We subject the sensor to a known field, measure its response, and use that to calibrate. And the way we tend to do that is by putting it in what's called a transverse electromagnetic mode cell, a TEM cell, which is basically just a parallel plate arrangement that applies a known electric field for a given voltage or RF power input. So we measure the response and can use that to calibrate. We can also use that measurement to determine the sensitivity of the device. So the definition of the minimum detectable field is the electric field amplitude at which the signal to noise ratio in a 1 Hertz bandwidth is 1. Right, so we measure the response to a given electric field, and then we measure the noise level in a 1 Hertz bandwidth. That gives us a signal to noise ratio, and we derate that based on whatever the applied field was to determine the minimum detectable field. So in this example, we had a signal to noise ratio of about 54.6 dB when we applied a field of 5.3 volts per meter. You derate that and you get a minimum detectable field of 9.9 millivolts per meter in a 1 Hertz bandwidth. And as you use a wider measurement bandwidth, of course the noise power will go up linearly with the bandwidth, which means the minimum detectable field goes up as the square root of the bandwidth. So this is usually expressed as so many millivolts per meter per root hertz. Right, so if you can measure this in a 100 Hertz bandwidth, then you would just have to measure this, multiply this by a factor of 10. You'd have about 100 millivolt per meter minimum detectable field. Right, so that's at the low end. And one more thing I wanted to point out about that. Notice how small this number is. Right, so the signal was, now you probably can't read that, but it's minus 73 point something. Oh, sorry, no, minus 79.6 dBm. And this really bothers people who work with RF. Like we talked to people about doing antenna measurements and so forth, and they're just not comfortable dealing with these low-level signals. And we try to tell them, well, all that matters really is the signal-to-noise ratio. We've got plenty of signal-to-noise ratio, but they just don't like it. We tell them, well, you can put in an amplifier if you don't like dealing with these low signal amplitudes. And they say, well, no, the noise figure of the amplifier will kill us. So it's easier to get people to consider this technology when they're measuring high field strengths. So here are some examples where we made measurements of a high-power microwave pulse source, the center frequency of 9 gigahertz. So now we're measuring fields up in the kilovolts per meter range. And that's high enough you can actually just do direct digitizing of the signal. So these are directly digitized signals. The one on the left at about 64 kilovolts per meter, you can see it has pretty faithful reproduction of the waveform. And if you transform that and look at the spectrum, you see you're just beginning to get a little bit of a second harmonic. Okay, so we're just kind of at the upper end of the dynamic range of the sensor. Whereas if we go to 100 kilovolts per meter, now you can see significant distortion of the waveform, and the harmonic is more significant compared to the fundamental. And this is one of these dipole sensors that I showed you a picture of earlier. So for this type of sensor, the upper limit of the dynamic range, roughly we would say it's about 50 kilovolts per meter. Another thing that's kind of interesting here, you see these little echoes, because these sensors don't care what direction the field is coming from. They only care what the orientation of the field is. But they will pick up the bounce as well as the incoming wave, which could be a good thing or a bad thing depending on what you're trying to do. Whereas if you're using, say, a waveguide, a metallic waveguide to capture the field, you're not going to get the reflections like that. And here was another interesting result that we saw. We had one particular sensor, and we were doing these measurements outdoors on a range in the high desert in California in August. Right? So we put that sensor out in the sun, and it just started drifting all over the place. But finally, it settled in. The X-cut sensors are more stable than Z-cut, which is subjective. You put them out in the sunlight, they're still going to drift. But eventually, they'll typically settle in. And this one happened to settle in right in the null. Right? It's right at the null bias point. And we got perfect frequency doubling. You can see in the spectrum, there is no fundamental, unless you count that little glitch there. Right? All the power went into the harmonic. And this can actually be useful, if you can control it, as a way of doing, say, true RMS measurements of pulse power. The first thing you have to do is square it. All right, another thing that people often ask us is, can we do a multi-sensor system? And the answer is, well, sure we can. In fact, that's one of the advantages of these fiber optic sensors. The sensor itself is very compact. It's about as big as my pinky finger. So I can easily cram a bunch of these in an array, and they don't really disturb each other too much since they're all dielectric. The question is then, how do you read out this array of sensors? Well, you could do a brute force approach. Each one has a separate laser and detector. Or maybe you have one big honkin' high power laser, and you split the power, but they still have separate detectors. Maybe you actively time multiplex the outputs from the different detectors. But there's also a simpler approach, which is passive time division multiplexing. You can just put in a fiber optic delay line after one of the sensors, put them into the same detector, and you'll see the responses of the two sensors separated in time. A foot per nanosecond, or actually about 1.5 feet per nanosecond of delay line. Right, so there's an example of my making a multiplex measurement. And of course, notice the response of the two sensors is quite different. They're sitting right next to each other, measuring the same field. But they may have different insertion losses, they're sitting at different bias points. So the amplitude of the response is going to be different. So you have to calibrate that kind of thing out. All right, the last example is a case where we made frequency domain measurements with a network analyzer and then transformed to the time domain. Right, so on the left, you see the frequency spectrum. And this was a case where we put a reflector about 1 foot behind the sensor. Right? So you see interference fringes between the incident and reflected waves. You transform that to the time domain, and you see two separate pulses. And these are only separated by about 2 nanoseconds, I think. Okay? So the fact that we can separate those closely spaced pulses is an indication of low dispersion in the sensor. Now, one Achilles heel of these sensors, as I mentioned, is the bias point dependence, and the fact that, especially with the electrode-free devices, they tend to drift a lot. And again, we tend not to want to do active bias control. We don't want to run electrical cables to the device. although we're thinking about other ways to do that. But what we can do is bias drift compensation. That is, we can measure the return optical power, and as that drifts, we can correct the sensor response to adjust for the fact that the bias point has changed. So here's an example of that. The blue waveform is the raw measured signal. And here, two things are happening. The sensor is drifting. This is one of these electrode-free sensors. They will drift over multiple cycles over just a few minutes. Right, so that's drifting like crazy. And at the same time, I was intentionally making large changes to the laser power. And I can correct for both of those things. And the red waveform is the corrected waveform. You see it works pretty well, except for this little region where the sensor drifted into the null. Because then there's no optical return power. There's nothing for me to use for correction. So it creates a little dead zone. But this was a very simple experiment using an Arduino microcontroller with only a 10-bit A to D. Better instrumentation, you could make this dead zone much narrower, but you could never get rid of it completely. All right, in the last few minutes here, I just want to talk about some alternative approaches we've explored, different materials and different device structures. So I mentioned the interest in thin film lithium niobate. And these are thin films based on crystal ion slicing, which I think I forgot to mention before, but that's how we do thin films in lithium niobate. Crystal ion slicing to exfoliate a layer from a bulk crystal, transfer it to another substrate, like, for example, quartz. And quartz, having much better RF properties, will behave better at high frequencies. Now, this was a sensor that did not have any waveguides in it. So it's not a guided wave sensor. Instead, it's based on prism coupling. So I showed you these pictures before, or these plots before, showing the distortion we got as we got to higher electric fields. Well, to avoid that, to get a sensor that responds better at high fields, you want to use something that has a shorter interaction length. So this is essentially a point interaction. Right? It's based on frustrated total internal reflection. It's a common technique that's used to measure the refractive index of thin films. Right? At just the right angle of incidence relative to the refractive index of this film, you'll get frustrated total internal reflection. You'll get a dip in the transmission. So he was using this, one of my colleagues built this sensor. He was using it as a sensing mechanism. Because as it picks up an electric field, the refractive index of this film changes, and this peak will shift a little bit. Oops. So here are some measurements that we made at above a megavolt-per-meter. And you see it's perfectly linear, right? No hint of a harmonic. I don't know, maybe there's a tiny hint of a harmonic there. All right, so not only did we show we can have a sensor that will withstand this electric field, but we can actually measure it because it's linear response there. Another program that we had a few years ago funded by DARPA was to investigate photonic crystals as electric field sensors. A photonic crystal just being, of course, a periodic dielectric material, which we do by putting a thin film lithium niobate slab on a substrate, because this really doesn't work in bulk crystals, because all the light just leaks into the substrate. And then you drill a periodic arrangement of holes, usually by focused ion beam etching. And here are some examples of devices that we made. So we did these devices with a ridge waveguide instead of a diffused waveguide. There's the photonic crystal device etched into the ridge, again by focused ion beam etching. And this device structure had a little gap here to function as a resonant cavity. So you should get a resonant peak transmission. And in fact, so our colleagues in France measured this, and they showed that they were able to see this resonant peak, and they were able to shift it by applying a voltage. And they're still working on that. Their latest idea is to take the photonic crystal and put it right on the end of an optical fiber, so you have a very compact sensor. I think I'm going to skip that one. And one more program that we had, sponsored by NAVAIR in China Lake, was to look at an alternate material called PMNPT. It's called a ferroelectric relaxer material. Its advantage is it has a huge electro-optic effect, like an order of magnitude higher than lithium niobate. Disadvantage is it also has an order of magnitude higher dielectric constant, so it's not clear whether those two things are a wash. But this was actually a bulk sensor, just based on polarization rotation. Depending on the orientation of an electro-optic crystal and what its tensor is, you launch a light polarized at 45 degrees, it will induce a retardation, which will cause the polarization to rotate, and you put an output analyzer basically to see a change in intensity. And again, here's a measurement we made at over a megavolt per meter, and again, very nice linear response. All right, so there are more details that I kind of redacted because I just didn't have enough time, but they should be in the PowerPoint under supplemental slides. Feel free to look those over and let me know if you have any questions about them. All right, so before I take questions, let's do the drawing. Did you pass in your slips of paper? Please pass those forward. The chairman will collect them. So while he's doing that, any questions that I can answer for anyone?